All right, so let's talk a bit math. That's what we're here for. About the math in this project. 99% of it. So, if you have a function defined in the integers, as you do when you do number theory, its Fourier transform lives on R modulo Z. That is, it's a function from R modulo Z to the complex numbers. R modulo Z, the fancy name for that is a circle. You can draw it in a circle. So that's why that's called the circle method. Now, why is that useful for additive problems? Well, if you have a convolution of two functions over the integers that way, then what is the Fourier transform of a convolution? Somebody knows? Yes, it's a product of the transforms. So, alright, so that's great. Because that means that, well, products are nice. Now, and why convolutions matter? It's because you can have that a convolution of three functions, f1, f2, f3, is non-zero at n, only if there's at least one non-zero term in the sum. That is, only if there's a way to write n as a sum of three integers at which all of the three functions don't vanish. So you just have to define these functions so that they are non-zero only if the m is a prime. And so if the convolution f1 star, f2 star, f3 star, well, that's whatever I said, if that is non-zero, that proves that n can be written as a sum of three primes. Right? So all we have to show is that that double convolution is non-zero at n. Now, how are we going to define f5? So Harald and Littlewood defined it to be, sure enough, 0 for n composite, and a funny thing for n prime. Log n is very easy to justify. It's there for a very good technical reason. It's because when you pick an integer at random of size about 10, the probability of prime is 1 over log n. Now, the exponential, depending on your perspective, you could see it as an artifact of their methods. They were pioneers in the circle methods, the ones who started it. Or you could see it as a very clever choice, which makes sense because they were first-rate analysts. We will later see why the exponential is very good, though not good enough. Alright, so we have to show that these triple convolutions, say f star f, is non-zero when n is bigger than say 10 to the 30, as I was, for the reason I was saying. That would solve the problem. Now, you can write any function in terms of its Fourier transform. So, as an integral of its Fourier transform, right? Yes, is there anything else? This is, a function is a transform of its transform. Now, the transform of its transform, alright, so this is its transform, the transform of a convolution, so it's a cube of the transform, as I was saying. So all we have to show is that this integral is positive. Once we show that this integral is positive, for n bigger than 10 to the 30, we will be done. So it turns out that, as in many problems in number theory, f hat is large when alpha is close to a rational a over q, with q small. It's as when you are tuning a radio. When you are tuning a radio, you are doing Fourier analysis over R, so it's harder than this. And when you get close to a radio station, you start hearing, oh, you know, then you get a very clear peak, right? It's the same. When the radio stations here are at 0, 1/2, 1/3, 2/3, the rationals with small denominators. Very well. So the idea is that you estimate very carefully. You want to get, you really want to listen closely to what happens in the radio stations at the alphas with small denominator, and then elsewhere, when you get noise, you want to at least bound the noise from above. And then the second, so this is what Harald and Littlewood were already doing, and Vinogradov managed to bound the noise from above, outside the major arcs. Major arcs being the arcs around rationals with small denominator. So the integral can just be decomposed as the sum over the major arcs and sum over the minor arcs. In the minor arcs, we don't know how to estimate things precisely, but we can bound them. So we take absolute values because we are pessimists. We also put a minus sign because we are still pessimists. And even if in spite of all of that pessimism, you get something positive, then you're done. Now, it's at this step and not before that the approach breaks down for the binary conjecture. So for the binary conjecture, everything works fine up to here. You just have f star f instead of f star f, right? But then the problem is here. You still have, it's the same function f, hat, so you still have peaks, but you see cubes sharpen peaks a lot, whereas squares sharpen peaks but less than that. So cubes sharpen peaks so much that even these very narrow peaks, because it's a really, the major arcs, don't be deceived by the name. They are really tiny, they are narrow. They are major because they are of major importance. But they are really narrow. So even if the integral, so with the cube, already the integral over the major arcs is bigger than the integral over everything else. Whereas for the binary problems, because squares amplify things less than cubes, the integral over the peaks is not quite as large as the integral of the absolute value over everything else. So for the binary problem, things break down at this point. That's why we are stuck, and we are still stuck for the binary problem. Very good. All right. So let us start with the major arcs. So in the major arcs, yes. So let us focus on estimating f hat of alpha for any given alpha in the major arcs that is close to a over q q small. There's also the issue of using this information efficiently, and that's non-trivial, but let us just focus on estimating precisely f hat of alpha from individual alpha. And we can express it as a linear combination of more complicated sums. Now, why on earth would we like to express f hat in terms of more complicated looking sums? So what is a complication? Here we have a character chi that is a multiplicative function from z modulo sum qz, q being the denominator here, so the complex numbers. It's because now q is hiding in that chi, and it no longer bothers your exponential here. In the Fourier transform, you have e alpha n there, right? But here you have delta n over x. And because the major arcs are really narrow, delta over x is really tiny. So this is a sum with a very slow phase. In fact, in practice, you go around the circle a bounded number of times. Maybe a million times, it's still a bounded number of times. Does that give you less cancellation? Is that bad? Well, you are in major arcs. You're not going to get all the cancellation you want anyhow. The function is back there. It is big there. You just want to show that it is what it is. And functions that have, sums that have a slow phase are easier to estimate. And that's a good thing. So the most efficient way, really, is to use the so-called explicit formula in analytic number theory. What does this mean? The term within brackets appears only when chi is principal, meaning when it's basically the trivial character. The small error is tidy, forget about that. Now, this mysterious sum, this is some of our rows. What are the rows? They are the places at which the L function, I will see, I'll remind you what it is, the L function vanishes. The L function is just a generalization of the Riemann zeta function for a non-trivial character. So it's a sum of chi of n times n to the minus x, where that converges and then you continue it. So it's a lot like the Riemann zeta function, it's just that there's one for every character. And everything interesting happens in the magical strip, the critical strip. They should have called it magical, but still, it's between real part between 0 and 1. Right? To the right of 1, where the series converges, everything's very boring, there are no zeros. To the left of 0, we know where the zeros are, they are called trivial, meaning we know that, and so they give you the small error. But the interesting things happen in the critical strip. So rho runs over all zeros in the critical strip. F delta, that's a Merlin transform of the weight function you chose, which you're going to choose so the problem becomes analytically easier, and also in such a way that the game will be rigged, mind you. So it's a Merlin transform of eta times the phase. A Merlin transform, it's an integral transform. So it's basically a Laplace transform, which is basically a Fourier transform. They're all the same. It is analytic on a strip, in fact usually a bigger strip. Very well. So the thing that is hard to estimate here is the sum. So what about these rows? So by definition, all the non-trivial zeros live in this strip. The real part is between 0 and 1. Now we believe, with ardent faith, that the real part is always 1/2. We believe that they are all lined up, right? Like ducks, in an infinite number of ducks, but still, yes, but that is precisely the generalized Riemann hypothesis, so it's unproven. So what kind of results do we have towards the generalized Riemann hypothesis? We know that there are classical zero-floor regions. These are really narrow forbidden regions close to the edges. So we know that there's nothing on the edges. So two kinds. And then we have a different kind of partial result. You see, there's one function for every chi, and for a given chi, for a given character chi, you can actually check rigorously by hand or by computer that up to a certain height, up to a certain imaginary part, all the zeros up to say 1,000,000, imaginary part up to 1,000,000, do satisfy the hypothesis. They lie on the line real part equal to 1/2. Yes. So actually the first one to do that was Riemann. He actually did the calculations to convince himself. He checked the first 3 zeros with his zeta function, the one for the trivial character. Now people can go further. But you have to do this, you can do this rigorously, but you have to do the work afresh for every character, basically. Certainly for every modulus. The problem is that zero-free regions are far too big to give you strong results, as in to give you a C small enough, say 10 to the 30. So you have to verify, you have to rely on verifications of TRH. So this slide will be the interesting computing bit. Checking the conjecture of the 10 to the 27, that's home computing. So up to where have people verified it for the Riemann zeta function? That is been verified up to very far up. The strongest claim is not rigorous, I'm prepared to say. The second strongest claim was careful, but I would call the third, yes, Platt's claim to be fully rigorous. He uses what is called what is called interval arithmetic. Interval arithmetic is when you're honest about the fact that the computer cannot deal with irrational numbers, really. In fact, it much prefers to deal with rational numbers as in the meaning of the powers of 2. So you really should be working with intervals containing real numbers, not with real numbers as such. And using that, you can, so Platt verified the RH up to, well, conductor 10 to the 5, and then I went around France mostly, and got computing time for Platt to do the check up to a bit further. In fact, further than I ended up needing things. So we know that TRH is true for Q for the modulus up to 200,000, or twice that for Q even, and up to a certain height. It actually decreases as P increases, because that's what I actually did need, besides being what you're in already. Alright, so we need that so that we can do the sum of a row, where F delta is Riemann transform. Now, if a single row has real part 1, or extremely close to 1, that will kill us. A single term of this infinite sum will kill us, because we want this sum to be much smaller than x. Alright, now if we check the RH up to imaginary part h, this imaginary part of rho, then the contribution of all those x to the row is tiny, because if rho has real part 1/2, x to the row has absolute value square root of x, which is tiny compared to x, provided that x is bigger than 10 to the 27 or 10 to the 30. Very well. Now, for t bigger than h, we know in essence nothing about the location of the zero. The zero-free regions are very weak, and our computer check ended. So the only way to win is for f delta of rho to be tiny. Alright, so we have to choose a category for this to be true. For f delta of rho to be tiny when the imaginary part is big enough. So you can show by stationary phase that f delta of rho behaves like the Fourier transform of eta, the smoothing function itself, without the phase, when delta is small. When delta is largish, well, say delta larger than 4 or 8, then the Riemann transform starts to behave much more like the function eta itself, with argument t divided by 2 pi delta. Now, so we need an eta that decreases rapidly, because f delta will be like it is when delta is large, and whose Riemann transform also decays very rapidly. Can anybody tell me what's the limit to that? I mean, why can we get a smoothing function that is wonderful from both points of view? Yes, exactly. Now, I will not put a picture of a cat here, I resisted the temptation, but yeah, so why did Harald Helfgott use that function? Well, maybe it was because it looks optimal. You see, the uncertainty principle, and in fact, Hardy had a hand in establishing this, tells us that eta and its Riemann transform cannot both decay faster than exponentially. So, and the problem is that e to the minus t, you could say, well, exponential is good enough for me. But no, because the argument for delta large is divided by 2 pi delta, and e to the minus 2 pi, e to the minus t over 2 pi delta actually decays pretty slowly. See, delta is a million. Even if we check the array up to 50 million, then t over 2 pi delta is going to be 8. And e to the minus 8 is a pretty big number. If you're going to add things to it and multiply it, it's going to go over one pretty quickly. It's over. So you have to do better. Well, nobody told you that you couldn't have a function that decays much faster than exponentially, and whose Mellin transform also decays exponentially. For example, the Gaussian. Obvious choice. It's funny that it hasn't been used that much in number theory, not at all, or almost not at all in explicit work. I really hope it will be used more. So we use it. So I had to spend some time, computing. It's amazing. It's a parabolic cylinder function, but people have not figured out the constants for that precisely, for the estimates. It's something that should be of interest to applied people as well, but, well, all right, so you do it. And so that's why you're allowed to use not just the Gaussian as a smoothing function, but any function based on the Gaussian also will get very fast decay in the Mellin transform. So what I mean by that is you can multiply the Gaussian by any band-limited function. Band-limited being something whose Fourier transform or whose Mellin transform decreases very rapidly. No, whose Mellin transform is completely supported. Yes, very well. And that's great, because you can mimic anything through g of t. You can choose g of t, but limited so that 8 of t is close to a picture of an elephant, if you wanted. An elephant who is a function, right? Very good. So the major arc problem is basically solved, because you get very good estimates, better than you need. But in fact, I left the major arcs for the last year of my work. I knew more or less how things would work out, but I was confident things would work out. I spent years and years working on the minor arc part, which was a much closer shape. You see, the problem with this is that it's very accurate, but because it's based on GRA verifications, it's valid only for delta and Q bounded. You're allowed to treat only a bounded number of major arcs of widths about a constant over x, or a constant over x times Q, and so everything else is minor arc. So you have to be much better at sort of metabolizing the rest of the circle. Not my metaphor, but you have to be better at eating cheese. So that's the deal. Now, as I said, the minor arc bounds are the most difficult part of the proof. I will not torture you with the technicalities, and it will be over in 10 minutes anyhow. But I will give you the main ideas of the proof. Yes, focus on the blue part. All right. Focus on the blue part. All right. There's one log x that is in the green, and there are no log x's in the blue part. A single log x will kill us, because log x over q will go to infinity as x goes to infinity, because q is bounded only by a constant. No log x's. There's only log q, one log q. Log q squared will be too much in practice. R is less than 1. And you also have that you have a suspicious delta 0, but the suspicious delta 0 is in fact good. Because as it gets bigger, it grows much more in the denominator than in the numerator, and delta 0 is always at least 2, and when delta gets bigger, it becomes bigger. Now, that corresponds to the fact that when you get away from the radio station, the signal becomes weaker. And that's reality, but that is about that reflects reality, that's also the minor arcs. And that's necessary, and that, I think having that before for other problems with several methods, but not in this context. And that's really important, because this allows you to have arcs of bounded lengths, in fact, decreasing them. So what are some of the qualitative improvements? One is cancellation within Won's identity. We will go that over very quickly. Then there's the fact, as I said, the error is your friend. For one thing, it's an argument, it appears it's an argument in a Fourier transform, and the Fourier transform of something continuous decays as delta goes to infinity. But there are also two other important things. Now, there's a relation, if I wanted you to take one moral, the moral of the fable is that the large circle and the circle method and the large sieve are really two sides of the same circular coin. Now, yeah, this is really important. So I have to improve several times in this classical tool called the large sieve, but then sometimes you want to use it as such, but you also don't want to see it as a black box. You want to take the ideas of the large sieve or of the version that you improved and put them back into the circle method directly, without forgetting about the large sieve, just taking the core idea and putting it into the circle method. And something that was maybe a bit overemphasized when I was a grad student was always smooth. So it was almost student abuse. And we were told to always smooth. People have big sticks. I would say smooth most of the time. Always consider smoothing, but different parts of the same problem may require different kinds of smoothing. So smoothing is essential for the major arcs, whereas the kind of smoothing is essential, whereas for the minor arcs, you just want a convenient smoothing. You want it to be continuous, but other than that, I ended up just using tau smoothing just for the purposes of comparison. But any kind of smoothing that you find convenient will do. Bond's identity is that. So Bob Wong talked about this at the ICM about 36 years ago. That simplifies Radov's original proof greatly, but it's a bit of a gambit. So in a gambit in chess, you gain a lot of flexibility. So what are these cutoffs, U and V? They are whatever you want them to be. Great. You can optimize it. But in a gambit, you also give up pawns. And pawns here are poison pawns, because pawns here are logs. So you lose 2 factors of log. But logs are precisely what will kill you from the beginning. And there was already one hidden log somewhere that I haven't talked about. So it's as if, and it gets even worse, because the first step in the minor arcs is Cauchy-Schwarz. And that's like attacking a hydra with an axe, because it becomes 2 different hydras that you have to kill in different ways. Very well. So, but it turns out that here you can recover at least one of the logs. The other log, as Tao had already showed, becomes a log Q. And then, well, at least in type 2, in type 1 it also becomes, you kill it entirely, and then you kill the other log that appears elsewhere. So it's basically all about killing logs. So the minor paper is of clear applicability if you like killing logs. Very well. There would have been other ways that I tried first, but this turned out to be the way I finished the job. So in type 1 sums, the first kind of, it's a very unimaginative name, but it's standard for this. You manage to get sums that look like, oh, there should be cancellation there, but oh, how am I going to do it without n functions? Well, in fact, you can do it, and this one is not too hard. The hard part there is to actually extract that sum. And then you can also improve on Radov's basic limits. I mean, it's a very great mathematician, but you can start, in fact, that's how I started. And then there's some in type 2 that really looks horrible. As in, yes, there is cancellation there, but how on earth are we going to get it without using n functions? And you are not allowed in this regime to use n function. But you can do it. In fact, you can show that you can bound this by a constant times m where the constant is smaller than 1. It's not 0.2. So 80% of the time, the inner sum is exactly 0. You can actually prove that. So you have to be very careful. So again, you have to focus on qualitative improvements, not on the constants, but you also have to be careful about those. And you also win a log just by using the version of the large different times. So how is the error our friend? Well, one thing is that when there is an error, it means that alpha equals to a over q percent over x. It's a good approximation, but not an excellent one, because delta is large. But Dirichlet guarantees us that every real number has a very good, an excellent rational approximation in a reasonable interval. So if alpha a over q is good but so-so, means that there's a different approximation, a prime over q prime in a larger but still reasonable interval. And so what you can do is you can just switch back and forth. Just decompose your sum and estimate some chance using a over q and some chance using a prime over q prime. And another thing, finally, a picture. So when you use a large sieve, the large sieve is basically an approximate Blanchabel identity. So a Blanchabel identity tells you that the integral of the square of your Fourier transform is equal to your L to norm, to your L to norm. But what happens if you don't have an integral, if you want to estimate the sum of the Fourier transform, its square rather, over certain angles? You have to know something about the distribution. Fortunately, you just need to know their separation. If they are separated by something, it's fine. The large sieve will tell you something. Now, if alpha is exactly a over q, then we just get some very neat separation. Say it's 1 over q. You get 1 over q, 2 over q, 3 over q, up to q minus 1 over q to 0. And then you have to stop, because q plus 1 over q would override 1 over q. And then you have to put the tray into the large sieve open, and then take the tray out. And then you have to put the biscuits again, and then, and so on. So it's a very good bound because the separation is big, but you have to multiply by the number of times you use the old one, and that can be a lot. Whereas if delta is large, it looks less neat, right? That's not because they don't know how to use xfig, that's because, you know, it's really, they get a bit bigger, and you have this gap. And so when you have that, it gets messy, right? You don't need a nut right here. But that's good, because that means you don't have to put the train reopened yet. There's a separation. A separation is good. Yes. So you can keep on putting biscuits in the spaces between the biscuits. That's good. And so only after around what? Only when you risk hitting this one do you have to put the train reopened. And you get a round that is almost as good as before. The separation is smaller, but it's just your arrangement from that. And you have taken an enormous factor, the factor of the number of times you would have used the order. Alright. And so you combine all of these ideas, you suffer a lot, and everything goes well for an Aug14Thu to 27. Or when we fall below that, and you don't want to make the proof too complicated either. Somebody ought to read it. In fact, the computer had gone up much further, and 10 to the 27 is something you can do in your own home computer in your own free time. And so you're done. So every odd number is times 3 primes.
Thank you very much. Are there any questions or comments? Actually, you finished 2 minutes earlier. We started 2 minutes earlier.
I was told 1 minute. 1 minute ago.
Okay. So, okay.
A lot. About 10 to the 9, roughly. Oh, a bit more than that. I haven't counted them, but fewer than 10 to the 10, more than 10 to the 9. Yes.
All were checked.
All were checked. All were checked. Some of the check for fixed Q can be parallelized. No, it can all be trivially parallelized, but in fact, for a fixed Q, you can do part of the check in one go for all characters at the same time. Yes. This was about 200,000 hours of computing time. And that up to not just 100,000, but 200,000. And in fact, 400,000.
Are there, we have, I will get 2 more questions, so are there any other comments or questions?
Yes? Who has a question?
Yeah, so you basically use...
We cannot hear you.
Hello?
Yes.
So you basically use GRH for finite Q, right?
That's right, for Q up to 150,000 in fact.
Was there any other applications for the finite?
Oh, I'm sure there will be. I mean, it's not copyrighted or anything. You can go and use the verification. Yes. There have to be. Yes, it's a general purpose computation.
Yeah.
So, we will get 1 more question. Is there anyone who this is your last chance? No? No?
Yeah, Mom.
Yes.
Do you have any thoughts at all about the real Goldbach?
The binary Goldbach.
Yeah.
I think it's really hard. I think, in fact, yes. I think if there's any hope of it in our lifetimes, it might come in part from work on prime gaps. Though even then, before people used to think that twin primes was just exactly as hard as binary Goldbach. In fact, binary Goldbach might be a bit harder, but at least there's a bit of hope for twin primes, and the two are not so far away. But I will not say that the main hope comes from this.
Okay, so I'm sure you have many questions, but he will be available, so you may ask him privately after the talk. So here is a present from local ICM organizing committee. So you don't have to open here. Thank you.